Hello guys, welcome back to MedZone African Motives. Still working on our power machines and 5 revisions, working on the steam turbines. That is how to end up drawing velocity diagrams in this case. So considering the question paper of November 2020, whereby we want to be talking about a condition where we are dealing with the steam discharges axially in this case, like what we are given here, that the steam discharges axially. Like I said, you're supposed to work on each and every part of the video. So make sure that you watch some of the other videos. And also, before we start, I just want to thank those who are part of the membership. If we are part of the membership, thank you so much for supporting our channel and for supporting our videos each and every time. Being part of the member, we are referring all these members that we see and others that are not showing here. So these are the ones that have got access to these videos that you'll be seeing, written members only. So make sure that you join the access or you join the membership family so that you'll be able to watch these videos to support our channel to grow as we need to reach others also, just the same way it happened to you guys. So supporting this channel means we are supporting others also. So you've got the access to the videos which are separate from the ones of others from the normal channel or from the normal channel. So make sure that you join, and also after joining we can link up to talk about what exactly is going to happen. The contact, as we can see on our description, our contact is displayed there. So once you join, it means you can contact on this number so that you can talk about the topics to be done or areas to be done. So the access is there. As we can see, the access is there on this join here. If you just click the join there, it takes the steps there, different levels that you're going to have: the basic math, the medium approach, the gigantic approach, the ultimate approach, all in one. Like it's a package, this one that you get, a package. If you're doing a course for N5, you get a package for that if you join in all in one. So that is what you're gonna have, and the peaks and so forth. So if you click the join, it takes you to the steps that are required depending with the how you are working from your side, but it gives you like the steps that you're going to take with your card number. So this is for the basic. So it depends with which part that you're going to choose. In this case, it is mine that I'm working with. So you just have to place your card number and so forth, depending with what you are working with. Okay, so you place everything there, then the steps will take you further to where you are going. All right, and that part you see it according to your device that you're using. So that's how you simply join. You have to choose on this part: is it basic, is it medium, is it gigantic, is it ultimate, is it the last part, which is the all-in-one, which is a package, which is a course that you are obtaining, a whole course that you're gonna have. So if you click the join, like I said, it takes you step by step until you join. All right, so that is it, guys. Thank you so much for our members for being part of the family. Those who are supporting this channel, by all means, I want to thank you so much for what you are doing. So sorry for disturbing our class, but I just found out that I need to thank you guys because you are doing a lot to this family. So much, you are doing a lot to us to grow every day. All right, question number 6, like I said, from November 2020 exam, which is on the steam turbines. We are given a jet is supplied, has a supplied kinetic energy in this case, which is the power. So this kinetic energy is the power, which is in kilowatts per kg. And we are given that steam discharges axially, which is the most important part that I want us to talk about in this class. Then we are given that the blade inlet angle is at 36 degrees, the blade mean velocity 235 meters per second, and the friction is 0.65, which is the coefficient of friction. All right, let us just take our information here. It's we are working with a condition where it discharges axially in this case, all right? So this one, it discharges axially, which is the most important part. I'm going to talk about this later on, but let us take our information here. We are given the kinetic energy, which is 227.815. So that is our kinetic energy in this case. So the kinetic energy given as 227.815 in kilowatts per kg. That's in kilowatts per kg. And also discharges actually, then the blade inlet. Remember, when you we talk about the blade inlet, this is the input that we are going to have here. That is the blade inlet, which is our theta. So we are given theta, which is the blade inlet of 36 degrees. We shall talk about that on the diagram. So that's theta, our blade inlet of 36 degrees. And also we are given the blade mean velocity 235, which is u in this case, the blade mean velocity. That was 235 meters per second. And the last thing that you are given here is the coefficient of friction, which is 0.65. So you're given K, which is 0.65. All right, so that's the only information that we have. And we are given that it discharges axially. All right, the first part of the question we're being asked in this case to calculate the velocity using the equation, calculate the velocity from 6.1. Which velocity are we calculating? We are calculating this velocity, which is the inlet absolute velocity, or the absolute inlet velocity to the inlet of our steam turbine in this case. So we are given a formula to apply, or a formula to use in order for us to calculate what? The velocity. So let us take our formula. We have the kinetic energy in this case, so 6.1. It was directly to the formula that we are given, since we said EK, which is kinetic energy, or is given there. They gave us KE, kinetic energy, which is given from the formula as the absolute inlet velocity squared over 2 in this case. So it was just a matter of playing around with what you're given. Substitute what you're given. We have the kinetic energy in kilowatts, which is 227.815 kilowatts. That's times 10 to the exponent of 3, which is equal to the velocity in this case squared over 2. So we can calculate our inlet velocity. From this, we can even cross multiply. This is same as over 1, so you're gonna cross multiply here. Thus this is gonna multiply the side, sorry for that. So 1 times the inlet velocity squared, that's gonna be remain like that. That's 1 times this. Then 2 is going to multiply this side, is 2 times this whole part here. So you multiply that part by 2, so it's just going to be 2 times 227.815 times 10 to the exponent of 3. So that's it. To remove the square, we can introduce the square root so that we obtain our inlet velocity. So that was our mathematical calculation in this case. So that means our inlet velocity is going to be 675,004, something like that, in meters per second. So approximately, just for our calculation, for calculation's sake, or when we are drawing the velocity diagram, it's important that we just play around with whole numbers in this case. So this is going to approximate to 675, since we've got a 0 which cannot change the 5, which is in meters per second. So that's an approximation that we're going to take for our inlet velocity. So meaning to say, on the information that we are given here, we can also add that we are also given the inlet absolute velocity, in this case, of 675 meters per second. All right. Now let's check what the question is all about here. The first part, the second part now on 6.2, it was to construct the velocity diagram in the answer book using the landscape format. That is, we are going to apply the landscape format, given a scale of 1 centimeter to represent 50 meters per second. Indicate the velocity values in meters per second on the diagram. 10 marks for that. All right. So we have the information that we are given here. 1 meter per second is going to represent this and that. All right, so let us just check. So this is 6.2. 1 centimeter according to the information that we are given is representing 50 meters per second. All right. So we are going to have a sketch. Let us have our sketch of the diagram, how it is supposed to look like in this case. All right. So on our sketch here, we are to consider that this is discharging axially in this case. When it is discharging axially, the exit absolute velocity is going to be taken at 90 degrees. Always it is going to be taken at 90 degrees. So meaning to say, on the exit here, we are going to have this at 90 degrees. So that is the whole consideration that is important when it discharges axially in this case. All right, we are going to have the exit at 90 degrees, meaning to say the exit velocity absolute is taken at 90 degrees from this point. All right. The whole part of the diagram is going to remain as it is. Remember your concept where we have got our inlet to the blade, which is our theta, the exit to the blade, which is our phi in this case. All right. Sorry, we've got phi there. Then we have got alpha, which is the inlet that we are going to have to the turbine, or we are simply talking about the nozzle angle, all right, the nozzle in this case, which is the nozzle angle. The inlet velocity in this case, this is our absolute inlet velocity on this side, being taken out at the exit at this point, which is the exit absolute velocity. Then here we've got the inlet relative velocity taken out as the relative exit velocity as it enters, then it goes out. So knowing your sketch is very important. Axially part is taken out at 90 degrees. So meaning to say, automatically on our sketch, we are going to have this at 90 degrees. All right. And let us check what we have so far from our diagram. Remember, we are given the velocity, in this case, that is the blade velocity 235. We also have theta, which is the inlet to the blade. So the inlet to the blade is 36 degrees. So on our sketch here, we can just indicate that this angle here is 36 degrees. All right. So this is just a sketch. We are going to draw it properly. Then also, like I was saying, we've got the blade velocity here of 235 meters per second. So our blade velocity here, which is U, is equal to 235 meters per second, which we are going to convert to centimeters from the scale that we are given. So we are going to divide 235 divided by 50 meters per second. That was going to give us 4,7. So we are going to obtain 4,7 centimeters, which is the length in centimeters that we are going to construct, 4,7 centimeters. All right. Then what else? We are also given here remember we calculated here the inlet absolute velocity, which is 675. So meaning to say we also have the inlet absolute velocity here. It's at 675 meters per second, which is in centimeters. We are going to divide again 675 divide by 50. So if we divide 675 divided by 50, we are going to obtain 13,5. So in terms of centimeters, this is 13,5 centimeters. All right, that is what we have from our sketch. And also we are given here, remember we've got the constant of friction or the coefficient of friction, which is 0,65. So from this coefficient of friction, remember I said there is a relationship between the coefficient of friction and the inlet relative velocity and at the exit. So the coefficient of friction is equal to the exit, which is over the inlet relative velocity in this case. So in this case, we do not have any one of these. We just know that our constant, our coefficient of friction in this case is given as 0,65. That is what we only know. We do not have the exit velocity. We do not have the inlet relative velocity. So meaning to say the formula for now is meaningless. So we're going to leave it like that. Let us do our construction. So we're going to need the ruler and our protractor. All right, so we have our ruler in this case, and we're going to need the measurement part of our protractor. So let us just keep this one aside. So from our sketch now, we are going to have the actual diagram. If we are to take note from our actual diagram here, we are just going to extend a little bit here so that we draw our reference line where we are going to have everything that we need in this case. So I'm going to present this as my reference line, but I'm not actually supposed to have this like big, okay, something like this. This can be my reference line. Then the rest of the line, you can just present it as a broken line. All right, so here just gonna have it as a broken line. All right, so on this reference line that we are having, we are going to measure 4,7 centimeters for the blade velocity here. So meaning to say you have a starting point here according to my allocations or according to this ruler that I'm using here. I'm going to mark at 0 and at 4,7, meaning to say I'm at 4,5, 4,6, 4,7. It can be somewhere there. So this is what I'm going to have. Meaning to say I'm considering this point and this point. That is where I'm having 4,7 centimeters to represent what? To represent our blade velocity. So meaning to say our U, which is considered as 235 meters per second. In terms of centimeters, we said it's 4,7. So we measured 4,7 on this line. So that's our reference part. So what we are going to need now is to measure, because what we know is that we are going to have 90 degrees going down, but there's no other part. We do not have this side. We also do not have this side. So it means for now, it's going to be meaningless for us to construct the 90 degrees. All right, so what can we do? We can construct the 36 degrees here because we can construct from this part to join along the 36 degrees because we know that our inlet to the blade is 36 degrees. So we're going to measure 36 degrees in this case. All right, so on the measurement, we are going to have something of this nature at the point, at this point here. So we are going to place it at this point so that we properly have our 30 degrees going in the clockwise direction. So that's 0, 10, 20, 30, 40, 50, and so on. So meaning to say 36 is going to be after 30. This is between 30 and 40 is 35. So just 1 point or 1 unit after that. This is where we have our 36 degrees along this line. So we're going to join from this point going this side. We do not know how big is this line that we are going to join. So here we are simply just going to join, but we do not know how big is this line that we are going to consider. So meaning to say you are supposed to be careful. The line is supposed to be bigger enough. All right. All right. So let me just have this way. All right. Sorry for that. So I'm just going to join these points here from this point, sorry, at the inlet of the blade here. So this is where I need the point that's joining. All right, let's try to have it on top here so that we can have a bigger line in this case. All right, so that's something of this nature. Okay, something of this nature here. So you're just going to join a bigger line because you do not know what's gonna happen and how big is this line. So just extend a little bit like this. All right, so that is what you're going to have, meaning to say we have got indicated the inlet theta to the blade, which is 36 degrees, which is going to help us now if we are to consider from the information that we have here. I want us to check what we are given here. You work with a sketch. You have constructed this line here for the, but you do not know how big because you do not have this value. So just leave it like that. Move on to the other part. What we know is that as we are to construct from this point here, as we are to construct 13,5 centimeters from this point to meet this line, they must meet at 13,5 centimeters. So meaning to say, you are going to this point here, measure 13,5 to meet the line. So the 0, this one, the 0 must be at this point here. So you're going to place the 0 at this point, stretch out or measure out 13,5, it must reach with this line that we are having of 36 degrees. In this case, they must reach at a certain point, which is in this case, all right, this is it here. So now, okay, let me put on top a little bit. So this is what you're going to have. So you're going to move your ruler so that where it is 13,5, remember 13,5 is here. So the 0 must be at this point, and you move until we've got a 13,5 meeting with this line. It must meet with this line. So I think somewhere here, 13,5. Yeah, let me do something like this. Yeah, something like this. We have 13,5. We're going to have 13,5 somewhere here on top, just a little bit. So that is where we are going to have our 13,5 somewhere there. So you're going to join now, because you know that from this point here, from our initial point, going up to this point, the distance there is 13,5. So where it meets with this point, that means we are having our reference condition according to the measurement that we are given. We can determine this distance here. We can determine it from our measurement. You can even measure the line. So if we are to measure properly in this case, that was going to be 13,5. Yes, 13,5 there. So that is our length. So we are going to obtain a length of 13,5, meaning to say our absolute input velocity, or the input absolute velocity in this case, in terms of centimeters, we got 13,5 centimeters. So remember, our scale is at 1 centimeter to 50 meters per second. So this value, are going to multiply it by 50 to obtain the speed now in meters per second. So 13,5, which is our inlet, times the speed that we are having, which is to convert in meters per second, is going to give us 615 meters per second. So meaning to say here, we are having 615 meters per second. But in terms of centimeters, remember, it was 13,5. So this is 13,5 centimeters. All right. So as you are constructing, you are building up your diagram. Also, you can even measure this angle here that we have. We can even measure this angle to say that if we place our protractor here at this point, we can measure going this in an anti-clockwise. That's 0, 10, and so on. So that is at 0 point. All right. So make sure that it is at 0 point. Okay. It must be at 0 point here, and also covering this line. So we're supposed to take our point a little bit big, a bit here. So the angle, this one is something like 20 there, but it's supposed to be a 19, all right? So you are supposed to take the angle that you have measured there. So if you are to measure this properly or accurately, this angle is supposed to be 19 degrees. That's your alpha. So you use the angle. If you're obtaining 20 degrees, use 20. If you are obtaining 18, use that 18, use the angle that you're obtaining from there. All right, so that's it. Let's check from our sketch. What else can we do? As we can see from our sketch, from this point up to here along the exit, we are moving at 90 degrees. So meaning to say, we are going to construct 90 degrees at this point. So 90 degrees, it's simply place it at this point here. So 90 degrees, that's direct straight along this line here. This is our 90 degrees. So you're just going to mark a point at 90 degrees. Then you are going to join going down. Remember, we said when it is going axially, we are going to have it discharging at 90 degrees, or we are going to have the exit taken at what? At 90 degrees. All right, so you're just going to join the points from this hue here, passing that point here at 90 degrees. All right, so that is the condition. So we do not know how big is this line. So just join going down as it is, just join going down. You do not know where it is going to reach. All right, so as we are moving down at 90 degrees at the exit, in this case, whereby we are referring to our beta here at the exit being 90 degrees. That's at right angle. All right. What is going to happen? How are we going to obtain this? Because we need to join from this point to any point so that we complete. So we do not have this length. So you do not just join to say, okay, I'm just going to join to this point here, or I'm just going to join here. You are supposed to know the length from this point up to this point, or maybe to have an angle. If you are given an angle, you measure that angle where it reaches the line. That is where you're going to have it. But in this case, we are not given the angle at the outlet of the blade. In this case, we are not given that angle. All right. So since we have taken this point when we joined to this point here, it means we can also measure the inlet, that we have the relative inlet velocity. So here we can measure our inlet velocity. Place your ruler to this point. So if you're to measure, you're going to obtain 9,3 centimeters. Meaning to say we multiply by 50, which is our scale, 1 centimeter to 50 centimeters. So if you multiply, this was going to give us 465 meters per second. We now have what? We now have the inlet to the relative. All right. With the inlet, why are we calculating this? Because we talked about a relationship that is happening between our inlet, the constant, which is the coefficient of friction in this case, K, to the exit and to the inlet of the relative in this case, that the coefficient of friction, remember from that formula that I listed, the coefficient of friction is equivalent to the exit relative velocity over the inlet. So we have the inlet relative. We want to know this exit part of the relative. So we can substitute, because we are given the coefficient of friction at 0.65. That is K 0.65. So we are going to take this 0.65 is equal to the exit, which is the one that we are supposed to calculate, over the inlet, which is 465 meters per second. So if we cross multiply here, that means you obtain the exit. So the exit relative velocity is going to be 0.65 times 45, which is going to give us 302.25 meters per second. So this is what we are obtaining. Then if we are to make a calculation in terms of the centimeters, now it means the exit is going to be 1 centimeter represents 50 meters per second. So you're going to divide this by 50 meters per second so that we obtain the centimeters, now the equivalent of the centimeters. So that was going to give us 6,045 centimeters, which is something difficult to work with. So approximately, we are going to work with the whole number on the centimeters part, because we need to construct this 6 centimeters. We now know the length that we are taking, which is 6 centimeters, and the exit we are referring, if we are talking about the exit, we are talking about from this point up to this point. This is our exit. So meaning to say, you are simply going to join from this point here, going 6 centimeters, 6,5 at 6 centimeters here. So you can even place 6 at this point. Then 0 must meet the line. You must meet the line at 0. From 6, we must meet the line like this. That's 6 and 0, something like that. All right. So if you measure like this, you must meet from this point to this line with the 6. It must be at 6 centimeters, and it must meet this line. Where it meets this line, that is the end point. That means we have our exit in this case. All right. That is how we can construct this part. So meaning to say inlet, then we have got our exit, which is at, we said 6 centimeters, which is 302. So if you take now to say 6 centimeters times 50 on the diagram, which is going to be 300, because you approximated to 6 centimeters. So you're going to have this as 300, but it was 302 there. So 300 meters per second. At 6 centimeters, we are presenting in terms of our diagram. To say on the diagram, we see 6 centimeters. That's why you can multiply by 50 to get 300. All right. But the actual value that we obtained is 302.25 meters per second for our relative velocity in this case. All right. So that is how you can attempt this question. So as you can see, we've completed our diagram. We can have the value of the exit as we've got our inlet absolute. We are going to have at the exit here as it enters exit. So we are going to have our exit velocity measure here from this point up to this point on your ruler. That was going to be 3.7 centimeters. Yeah, 3.7 centimeters. So from 3.7 centimeters, we convert to meters per second. From 1 centimeter is 50 meters per second. So we multiply by 50. So if you multiply 3.7 by 50, you're going to obtain 185. So that was going to be 185 meters per second. So that our exit velocity, in this case, absolute velocity. All right. And if we are to join horizontally from this point, making sure this is horizontally at 108 degrees, we are going to obtain the wheel velocity in this case. All right. So we are going to have the wheel velocity measure from this point to this point. You are going to obtain 12.3 centimeters. Then you convert to meters per second, multiply by 50. We have this in meters per second, which is going to be 615 meters per second, right? Then the other thing is to have our flow velocity at the inlet and at the exit. So at the exit, our flow velocity is the one that is corresponding with what? With the exit absolute velocity, meaning to say these two, they will be equal. They're taken from the same point. So meaning to say our exit flow velocity, all right, let's see here, all right, our exit flow velocity is going to be the same as our absolute exit velocity in this case, which means at 185 meters per second, 3.5 centimeters, all right? Then the last part that we can find also on this diagram is the inlet. At the inlet at 90 degrees, this must be perpendicular. So you take it at 90 degrees from this point. You have your inlet flow velocity in this case. So if we were to measure our inlet flow velocity in this case, we were going to obtain 5.5 centimeters. If we were to measure, we're going to obtain 5.5 centimeters, multiply by 50, so that you convert to meters per second. That was going to be 275 meters per second. So we have completed everything on our diagram. All right, we are left with this angle here at the exit of the blade, in this case, the exit. So by just placing our protractor, just like the previous part, we can measure this angle. So if we place this at this point, we are going to measure this angle in the anti-clockwise direction. So this angle is supposed to be 38. Yeah, 38 there. This angle there is 38. All right. So the angle is supposed to be 38. So that's our exit, which is our phi. That is 38 degrees. So that is a phi. So that is it. That is it, guys. That is it. That is, you can obtain 10 marks. You've got 10 marks here. You've got 10 marks automatically. All right, so let us consider our questions. Our questions now is, all right, we've got a lot of things here. Okay, no problem. 6.3, 6.31, using the velocity diagram in question 6.2, determine each of the following: the nozzle angle in this case, which is our alpha to the nozzle. In this case, we measured this already. Remember, I said alpha there is the nozzle angle, and we measured this. We got 19 degrees. So that's 6.31. Our nozzle angle alpha is 19 degrees. And also, we are asked here to calculate or to state the relative outlet velocity in meters per second. Also, we calculated this, the relative outlet velocity, which is 6.32, sorry, 6.32. So we're given to calculate the relative outlet, which is at the exit. So at the exit, we obtained here. So you can take this value, 302 meters per second, or you can take the one that you, because when you constructed 6 centimeters. So on our diagram, 6 centimeters corresponds to 300 meters per second. If we multiply 6 times the scale of 50 meters per second, we obtain 300 meters per second. So you can use the one on the diagram as we are instructed to use the diagram. So it's going to be 300 meters per second. All right. Then lastly, we are asked to calculate or to find from our information the total wheel velocity. The total wheel velocity, we already have it from our diagram. We measured this part here, the wheel velocity, 615 meters per second from 12,3 centimeters that we obtained. So meaning to say we have the wheel velocity, the total of it, which is 615 meters per second. So these are the typical questions. That's how we might be given questions when it is discharging axially. The most important part that you need there is at the outlet, at the exit there, you are taking this at 90 degrees. So meaning to say the exit absolute velocity was taken at 90 degrees. That is how you are supposed to have this diagram. So let us continue to revise as much as we can and keeping on to support our family. And like I said, make sure that you become part of the family, become a member of the family so that you have access to unlimited questions. Join for membership so that you can watch any video. As you can see, these typical videos like this, they will require you to have a membership so that you can be able to watch them. So please make sure that you join. By joining, you can have access to any part. It can be, I don't know, as long you are working with any part that you're given there. So let's try to revise as much as we can, guys, as we prepare ourselves for the exams which are ahead of time. For now, that's it from Maison African Motives till we meet again.